reactions have a specific mechanism by which they occur. And so the mechanisms that we're studying now are classified as ionic, which means two electrons are moving. And so it's kind of subtle, but that's what that double-headed arrow means. It's single electron, that's radical, and then it has sort of a fishhook-looking arrow. But as we'll see today, the SN2 reaction has a lot of complicating factors. And what I mean by that is we're going to look at stereochemistry, the carbon bearing the leading group. We'll look at the nature of the nucleophile. Again, the nucleophile is a Lewis base that's supplying the electrons. The electrophile is a Lewis acid that's accepting the electrons. And then we have to consider things like solvent. So all of these things are now sort of coalescing for us in how the reaction proceeds. So the other thing to mention, the 2 in the SN2 is bimolecular, and that deals with the rate of the reaction. And so all of that, again, is going to tie together when we look at the nature of the electrophile, basically the classification of the leading group. If the reaction will go fast, slow, or it won't work at all. So now that we're sort of getting into the meat of organic chemistry, you're going to see there's a lot more detail and nuance to things we have to consider. So today, again, we're going to look at stereochemistry, nucleophiles, solvents. We'll do some problems to sort of put this together. On Friday, I believe, we're going to start the other substitution mechanism, which is SN1. So again, when you see those things, that should elicit in your mind sort of the visual about how the reaction is occurring. Any questions before we get started? So, as we're studying this, you always want to keep in your mind these vocabulary words. I'll write them here. So nucleophile, electrophile. Those are the terms that we're going to use for things that are supplying electrons or accepting. And in terms of the Lewis definition, the nucleophile is a base, the electrophile is an acid. Now, what you have to keep clear in your mind is that these are not proton transfer reactions like you're used to seeing in general chemistry for an acid-base reaction. So under the Lewis definition, we're talking about the electrons and how they move. So again, that arrow, that double-headed arrow is indicating the movement of two electrons. And overall, the process is ionic because you're dealing with plus charges and minus charges. So just be clear, the CH to C chlorine or C bromine, that's radical, and the arrow looks different. So we had left off on Monday about the class of the electrophile and how that relates to the rate of the reaction. So the nucleophile is supplying the electrons to form a bond to carbon, bearing the leaving group. So that carbon bearing the leaving group, that's your electrophile. The rate is primarily determined on the class of that electrophile as shown in the first column. So if we compare bromomethane, bromoethane, and 2-bromopropane, the 2-bromopropane has a benchmark, a rate of 1.
bromoethane is 50 times faster, and bromomethane is 1,000 times faster. So again, the reason is when we're looking at the sigma star, the antibonding orbital, in which the nucleophile is supplying electrons, it deals with the steric bulk around the carbon atom. So if we're looking down that bond, the blue ball is basically indicating the antibonding orbital. And so the carbon bearing the leaving group, if it has 3 hydrogens, that orbital is pretty accessible. But as you start substituting methyl groups, you'll see that area on this space filling model. So the white thing is the hydrogen. Now if we substitute for a methyl, you'll see that area decrease. And then now we have 2 methyls and then 3 methyls. And you can, at that point, the area is pretty small, you barely see it. So it's really about accessibility of the lone pair to that orbital. So under these reactions, or the SN2 mechanism, if you have a tertiary alkyl halide or leaving group, that's essentially not going to react. But we're not off the hook yet because you can still do substitutions there. They just go through a different mechanism, SN1. So it stands for substitution nucleophilic, and now the 1 means unimolecular. And again, that deals with the concentration of reagents. So that mechanism is very different from the SN2. And then one last class of leaving group that we need to think about is called neopentyl. So that word right there. Again, pentane is 5. A neopentyl carbon basically will have this group on it. So see that tert butyl, that's 4. And then it's bonded to that 5th carbon. So that's called neopentyl. And even though you would classify that as a primary bromide, if you look again at that space filling model, you can't really see the antibonding orbital. So that tert butyl group makes it really hard for the nucleophile to attack that carbon. So that's a special case to look out for when doing the sort of rate comparisons. So again, as we're thinking about, going into the final exam, and you get these questions of, which of the following will react the fastest or the slowest, I like to just make things easier for myself to put them in like a trend. So this is the trend for SN2 substrates. Again, methyl will react the fastest, followed by primary, secondary, and tertiary will not react by SN2. Things being what they are, I don't have a gray highlighter, but the secondary one is the one that takes a little bit more of diagnosing the reaction conditions, because the tertiary will always do SN1, Methyl primary always do SN2, and the secondaries can do both. And the way you determine it is the reaction conditions. What's the nature of the solvent being used, the nature of the nucleophile. So you have to understand the reactivity of those things to determine if a secondary one goes through SN2 or SN1. And as we'll see today, the reason that matters is one of the big issues is stereochemistry. So as an example of this, the question is asking you, under SN2 conditions, which one of these four will react the fastest? And the strategy for solving this is always convert a name into a structure because it's visually easier to classify things. So we'll do that. We'll classify then, I think these are all bromine. I think there's one iodine. We'll classify the nature of the carbon bearing the halogen, and then we'll think back to that trend. So that would be 2-bromobutane. This is 2-iodo-2-methyl propane. 1-bromo-2-methyl propane, and then 1-bromobutane. So we've drawn them out. Now we can classify them. So 2-bromobutane, we would say that's a secondary bromide. So that carbon is bearing 1-2 carbon substituents. 2-iodo-2-methyl propane is a tertiary halide. 1-bromo-2-methyl propane, that's primary. And then 1-bromo is primary. So right away, we can see that we're really dealing with choices C and D. But the difference between them, if we look to the carbon next door, so that's the carbon bearing the leaving group. This one has that extra methyl group, and again, that's some steric hindrance that's going to slow down the rate at which the nucleophile can attack that. This carbon only has the one carbon group and 2 hydrogens, so that's going to be a little bit more accessible. So our answer for this would be D. The next question is just calibrating you to the end of that question. So in terms of assigning the class, so if we look at this at choice B, so that's the carbon bearing the leaving group, which is iodine. From that carbon, you're counting the number of carbons attached to it. So you have 1, 2, 3. So secondary, tertiary, primary, and primary. So now the slowest one would be choice B, because that's tertiary. Yeah.
Is iodine a better leaving group than bromine? So for instance, if there's like 1 iodo-butane and 1 bromobutane, which one would be faster?
So we'll look at that more explicitly today, but if you had the same sort of carbon backbone, but the leaving group changed, in that case, the iota would be the better leaving group. And we'll talk about why that is, again, in relation to the pKa argument. So a lot of things can be correlated back to acidity. So that's basically a good lead-in for this slide. The question is, what makes a good electrophile? And so the connection here is, again, the electrophile has the leaving group. So as part of the mechanism, the leaving group is always taking with it the electrons in the carbon leaving group bond. So what makes a good leaving group is the ability of that atom to accept those electrons. And in the case of the haloalkanes, as shown here with, notice that part's not changing. It's all methyl, and what's changing is the leaving group. So when that bond breaks between carbon and X, where X is the halogen, that's what you're forming. So that the halide with the negative charge. And so we then relate that back to looking at the conjugate acid of that. And then from the pKa values, which we just get from the table, really the line is right here. So the ones in green are all good leaving groups. The fluorine in red is a bad leaving group. So the pKa value of that conjugate acid, really you're looking for that value to be less than 0. Because we know that the stronger the acid, the weaker the conjugate base. And the way that ties into this is that means that conjugate base is very stable. Another argument that's used is the bond length. So iodine is a better leaving group than bromine because the bond length is longer, and then iodine is much bigger. So when you're going down the group in the periodic table, the size of the atom increases. And so another factor in that is called polarizability. And the way that I think about it is, like, fluorine is sort of like a golf ball. It's small, it's very dense, its surface is hard. Iodine is sort of like a Pikachu pillow you stuff under your arm. It's big and fluffy and squishy. That's what polarizability means. So iodine can accept those electrons and be okay with that. The carbon-fluorine bond is small, it's very tight and polarized, and it does not want to break. So one reaction that I'll show on here, but that's not indicated in the slides. It's called halide exchange. So it occurs through SN2. So if you had chloromethane, you could treat that with sodium iodide to make iodomethane. And so you're exchanging one leaving group for another that you can then use the iodide as the better leaving group in a subsequent reaction. And you might think, well, if chlorine's fine enough, why would I need to do this? Remember probably the lab you hated most in Gen Chem was the product solubility constant. You took these solids and dissolved them and see how much dissolved. So in this class, we're primarily concerned with the organic product. But when you're in lab and you're doing things, the nature of that inorganic product can matter as well, because that will have a solubility profile that you can use to your advantage. So for example, we know sodium chloride is table salt. So you can choose a solvent that's going to make that precipitate out much faster, and then you can get your reaction to happen within a reasonable time frame. So with halogens, you're typically looking at iodine, bromine, and chlorine. And so you wouldn't want to use fluorine as a leaving group. The other thing you can't use as a leaving group is OH minus. So if you took methanol and you added sodium bromide, that bromide would not displace OH minus, so generating sodium hydroxide. And again, the reason for that is the pKa argument. So the leaving group is OH minus, the conjugate acid is water, and then see that pKa is 14. So that's not less than 0. So OH minus is a bad leaving group. With that said, you can do a transformation where you take OH and you make it into a good leaving group. And so that's shown on the bottom reaction. So we have methanol again. And notice what we're doing is the oxygen is still retained, but now we're basically substituting the H part for this other group. And so that's called a sulfonate ester. I'll write a little bit of the mechanism in a minute, but the reason that is now a good leaving group is because it resembles sulfuric acid. So we know that sulfuric acid is a strong acid, and so when the nucleophile attacks that, you break that CO bond, you get that conjugate base. That's a nice stable conjugate base as a leaving group. And so you've activated the OH to the sulfonate ester, and now you can displace it. Some instructors, I don't necessarily use this term a lot, but what happens is that oxygen needs to bond to that sulfur. And some people will explain this as like lasso chemistry. So you're lassoing out HCl, you're forming an OS bond, and then you have your sulfonate ester. So the reaction produces HCl, and this base triethylamine is in there to neutralize that. And so you get this salt that's formed, and that will typically crash out of solution. Yep.
Once you break that chlorine hydrogen bond, the hydrogen that's on the OH, that oxygen that's remaining will fuse to the sulfur.
Yeah. Yeah, so I'll color it in. Maybe I'll just use blue. So that oxygen is retained right there. And so basically this whole thing is the leaving group. And so on the next slide, what we'll see is that R that I just highlighted in red. What is the nature of R? What can that be? So with that active ester now, that can do the SN2 reaction, and so you've substituted that leaving group for bromine. So the nature of the R group is shown in the table here. And I guess I'll just draw those out so we can see what they look like. So that's the first one, that P tall. So the R in that case has a benzene ring that's substituted with a methyl group. The reason that this would be used, practically speaking, have you guys done thin layer chromatography? So that benzene ring allows you to see the molecule under UV light. So you put your TLC plate under there, you can then see it. So methanol, if you put it on a TLC plate, you wouldn't see it because there's nothing with double bonds in it. The double bonds are what accept the photons, and you get transitions, and then you see it on the plate. And again, that concept we'll cover in Organic 2. The next one, the R group, is just methyl. And then the last one is the mother of all leaving groups. It has a CF3 group instead of CH3. So CH3 and then CF3. Those fluorines make that. That's sort of the best leaving group you can get in organic chemistry. These would not be UV active because they don't have that aromatic ring. If you get into the nitty-gritty of organic synthesis, you would say, well, why would we use this if we can't see it? People will study the number of atoms in things. So see how that's 1 carbon. And then over here you have 7. So this is going to have a higher molecular weight, which means the byproduct is higher molecular weight that you eventually have to purge. And if you're doing this, if you're trying to make metric tons of something, you don't want to be generating a waste product that is higher molecular weight. Because at some point you got to get rid of it. And the community, which the company exists, probably don't want you dumping it into their water table. So those things eventually will matter. But for just learning the concept, you can use any of these and it'll be fine. So that's the nature of the electrophile, the carbon bearing the leaving group. The next big thing to talk about is the solvent. So the solvent is another chemical, so it's typically a liquid. And when you have reagents, they have to mix, and so they need to be in solution so that when the reaction occurs, the reaction's actually a collision, right? The nucleophile is hitting the electrophile, so that collision. So things have to be in solution. If you take two solids, the reaction's really never going to work. So the solvent solubilizes things. It also serves some other purposes. One is a heat sink or a heat source. So if you dump everything in at room temperature, so 25 degrees C, and nothing's happening, from the Arrhenius equation, you can start increasing the temperature. So you can go to 35 degrees, 45 degrees. Eventually, you'll hit enough energy that you overcome the activation barrier. Or if the reaction itself is producing heat and it's like runaway heat, where it's too much, the solvent will absorb that and sort of dissipate it that way. So the solvents, the chemicals that are listed are the most common ones for SN2. And so in the first column, you see their names. Below, you see the structures. And what is unique about these for SN2? They have to be polar. And I'll draw some delta pluses and minuses on them. The other thing they have to be is aprotic. And that basically means there's no alcohols or amine groups in them. They have to be polar because the transition state is polarized. You have delta pluses and delta minuses. The solvent helps stabilize that. And the reason you want it aprotic without OH or NH, those groups will slow the reaction down. So what I'm saying to you for SN2 is going to be sort of the opposite for SN1. So the nature of solvents for SN1 is going to be different. So we'll just walk through these. So acetone is the first one, and you'll notice the arrow here, it says increasing dielectric constant. And that's a number reported in the last column. So the greater that number, the more it facilitates the reaction to occur. So it'll occur faster. So acetone, what's nice about it is it's the lowest boiling one, right? So it will typically help the reactions proceed. And then when the reaction is done, you have to get rid of solvent. So you want that to be as low boiling as possible to get rid of it. Higher boiling solvents, they work well, but they're practically speaking really hard to get rid of. So what do we mean by polar? So oxygen has its lone pair. So that's delta minus, that's delta plus, so that's the polar. Notice that nowhere in there are OH or NH bonds, so that's aprotic. The next one is called HMPT or HMPA. That stands for hexamethyl phosphoramide. That has the highest boiling point, and then the next highest dielectric constant. I don't tend to use this in lab because that boiling point is so high, it would be a nightmare to get rid of. Even under a vacuum distillation. So you guys did boiling point and distillation in lab. You're probably separating mixtures like binary or ternary mixtures. So you probably had stuff that was under 100 degrees. Once you get up into like 230 degrees, it's really hard to maintain temperature that hot. And then again, that vapor has to flow through glass, which is cold. So your heat source has to be like super hot. And then what can happen is it can get hot enough to the point where the glass will just break. And then you're sort of screwed. So the higher boiling ones we tend to just avoid. Acetonitrile is a nice solvent because it's under 100 degrees boiling. Again, it's polarized. So delta minus, delta plus. DMF is dimethylformamide. And then the last one is DMSO, dimethyl sulfoxide. The other nice thing about these solvents is they have fairly simple, unique proton NMR spectra, so that when you do analyze your product, you know if they're still in there or not. Any questions on the solvent? So the reason, again, that they're aprotic is as shown in this little figure here. The nucleophiles that we're going to use are typically negatively charged. And then they're balanced out by a positive metal cation. So we see that here with M+. Because the solvents are polarized, the negative charge will help stabilize that positive charge. And then even though this is a cheap drawing, if you think in 3D, there's a lot of solvent molecules around that metal. And so if they're solvating the metal, that means the nucleophile is further away. And it is then able to supply its electrons to do the reaction. Then the other part of it is that byproduct that's formed, its solubility in the solvent that you're choosing. So solvation of the metal cation is important. When students are in my lab and they're doing this sort of thing, I just say, we'll start with acetone because it's easy to set up, it's easy to strip the solvent off after and figure out if things worked. So as I said, the SN2 reaction has a lot of stuff you have to keep track of to make sure the parameters are right to get the reaction to proceed at a reasonable time frame. And so now the nucleophile, as I said, it typically has some metal, and then the nucleophile is negatively charged. So it's an ionic compound. For the most part, all of the nucleophiles will be soluble, even though they have that ionic bond. They are soluble for the most part in the solvents we listed. So what makes a good nucleophile? The trend runs opposite of electronegativity. So we know that fluorine is the most electronegative. So the blue arrows are showing you the run towards fluorine either across the period or up the group. And then the red arrows are showing you how nucleophilicity increases. So just in that first period there, based on the trend, carbon-based nucleophiles are better than nitrogen. And then going down the group, silicon-based nucleophiles would be better than carbon. So in comparing a nucleophile and its conjugate acid, the species with the negative charge is almost always better in SN2, and then the neutral conjugate acid is better in SN1. And again, the reason for that is the negative charge species has that lone pair exposed already. It's ready to form that bond to the electrophile. Because SN1 is unimolecular and it reacts through a different mechanism, the neutral species is better for that. I think this is the Incredibles. Am I recalling that right? So now that we're a little educated, we know the difference between nuke attack and nuke attack. So in the fill in the blank here, or the chem Mad Libs, it's probably not as exciting. In an SN2 reaction, the blank supplies the lone pair of electrons. So that's nucleophile. To attack the electrophile, at a trajectory of 180 degrees to the leaving group. So, as I said, we're going to learn a lot more mechanisms. So it's important to know, like verbally, how to describe it, and then what that description means in terms of the arrow pushing. So over the next run of slides, we're going to look at the individual elements and what nucleophiles they're present in. Yeah. Say it again. I don't think so. I'd have to think about some scenarios to give you a more confident answer in that. I guess I can't think of anything specific to calibrate that, but perhaps on Friday I'll try to draw up a slide to address that. So over the next couple of slides, we'll just move across the periodic table, look at carbon, nitrogen, and oxygen nucleophiles. And so again, these are the way you get those elements into your molecule. So the first one is called cyanation. And so that's going to introduce the nitrile functional group into the molecule. So potassium cyanide. That will displace the bromine, do the substitution, and now you've introduced the nitrile. And so that gets the carbon in there, and so that you're not forgetting. We would use IR to identify that C triple bond N has been incorporated in the molecule with that stretch from 24 to 2200 wave numbers. So another carbon nucleophile is the alkyne nucleophile. So again, this is an sp hybridized carbon. So you're adding 3 carbons into that molecule. You'd end up with 4, and so that molecule would be now 2-butyne. So those are 2 ways to get carbon into a molecule. Inorganic 2, we'll learn about other ways, but you need to go through many more modules before we learn those reagents. So nitrogen nucleophiles. To preface this slide, you cannot use ammonia. So there's ammonia NH3, and it has its lone pair. So it would attack that carbon, the bromine would leave. That would generate methylamine. But now the issue is that nitrogen still has a lone pair, and it's going to be competitive for reacting with the bromomethane just like ammonia is. There's no way of saying, okay, I just want methylamine, please stop. It's not going to listen to you. So now you have ammonia in there, you have methylamine. The methylamine will react to form dimethylamine. That still has a lone pair. That will further react. Now you have trimethylamine. And that will further react again to get you the salt. So this would be a bad reaction because you're going to end up with a huge mixture of products. And anytime you form a mixture of things, you have to separate it, and that takes time and effort. So do we just forget about nitrogen, pack it up and go home? Not so easy. That lone pair on nitrogen is the issue. So the reagents shown on this slide are a workaround to that. So the first reaction is azidation. So you have Na plus, N3 minus. And so that's going to form an azide. And you would, again, see that in the IR. In the same region as the triple bond. So that nitrogen is no longer, the nitrogen bonded to the carbon is no longer reactive. It won't go after the bromomethane to incorporate another methyl group. So it's essentially oxidized or protected, so that if you did want to make methylamine, and this is something we'll learn in Organic 2, you have to do a reduction. So the reduction takes the azide to the primary amine. So really it's a two-step process to get to the thing that you want. So a lot of organic chemistry, especially in Organic 2, are based off named reactions. So the Gabriel amine synthesis uses this reagent that's shown, which is called potassium thialimide. And so that nitrogen is going to have two lone pairs. It'll be negatively charged, and then the potassium's plus. So if you look at the reagent, when I say it's protected, it has nitrogen-carbon bonds. And one of these lone pairs is delocalized through resonance into the oxygen, so it's not reactive. Then the other one is the nucleophilic pair. And so this is a way of incorporating nitrogen into the molecule. And the lone pair that's left over is non-nucleophilic due to resonance. So the nitrogen's protected, and then to deprotect it, you have to run another reaction. But that gets it into the molecule. Any questions on nitrogen? Yeah. So it's protected because that lone pair, which could be nucleophilic and react with a second molecule of bromomethane, the lone pair is delocalized through resonance. So it really doesn't exist on nitrogen anymore. And so it can't go through another SN2. Yeah, the solvent is the medium the reactions run in. The temperature gives you an idea of where you need to be to get it to go. Again, normally if you're doing this in lab, you just start at room temperature. You do some TLCs to see if the product is forming. If it's not, say after an hour, then you start raising the temperature. So I think we have enough time to do the oxygen and then one or two questions. Yeah.
The solvent for each of these reactions.
So for oxygen, another named reaction is the Williamson ether synthesis. And again, where the lines are going to start getting blurred, you know, especially now until module 5, is really with this type of reagent. So sodium methoxide is a reagent with O minus. And you have to diagnose the conditions to determine, is it acting as a base, which will abstract a proton, or a nucleophile, which is forming a bond to carbon. So under these conditions, it's going to do SN2. So Na plus, O minus. That will get us the displacement to generate now an ether. So as the name says, it's always going to generate an ether. If you wanted to make an ester, you would use the salt of a carboxylic acid. So this is probably one where temperature is really going to matter. Again, because that conjugate base is pretty stable, meaning that it really does not want to participate in this reaction. So you have to heat it quite a bit. And again, if you've ever made spaghetti at home and you've boiled water, and you put your hand over that steam, I mean, it gets pretty hot. So as you're approaching 100 or above, you know, your reaction vessel is getting pretty hot. So once that oxygen displaces the halogen, now you have your ester functionality. So again, overall, we call this functional group transformations. And then always keep in mind, you know, IR, mass spec, NMR, how you identify those new functional groups. So let's do one question before we wrap up. So if you are given 4 electrophiles and then 1 nucleophile, which one of those would react the fastest by SN2? So the structures are drawn. Next thing we do is classify them. So that's secondary, primary. C is because that's sp2. And then D is also primary. So now we're between B and D. This one is special because it's allylic. So that will win because that carbon-bromine bond in the allylic one is a lot weaker than the one in B, which is a normal primary. So we're about out of time, but again, I think you can realize with the nuance of all these details, things are getting a little bit more complicated. On Friday, we'll finish up the stereochemistry part of SN2, and then we'll start SN1.